Alright, so we're finally in the beginning of Chapter 3, and this is Section 3.1. The first thing we're going to be talking about is something called the power rule, and it tells us how to take the derivative of f of x equals x to the n. First, we're going to consider the case where n is a whole number, a positive whole number, and then we'll see that the power rule works in general for any value of n. So first, let's look at the derivative of x squared. And this is something I believe we've done a couple of times, but let's do it again. F prime is by definition the limit as h goes to 0 of f evaluated at x plus h, so that's x plus h squared, minus f of x, which is x squared, all divided by h. When I multiply out x plus h squared, I get x squared plus 2xh plus h squared. The x squared and the minus x squared cancel out, and the rest has a factor of h, so I'm left with 2x plus h quantity times h divided by h. My h's cancel. I'm left with 2x plus h. When I plug in 0, I get 2x. Let's try x cubed. So the derivative is the limit as h goes to 0 of f evaluated at x plus h, so that's x plus h cubed, minus x cubed over h. When I multiply out x plus h cubed, there's a formula which gives me x cubed plus 3x squared h plus 3x h squared plus h cubed, minus h cubed over h. My h cubes cancel out, and the rest of the terms have a factor of h that I can pull out, leaving me with 3x squared plus 3xh plus h squared quantity times h, all over h. The h's cancel, leaving me with just 3x squared plus 3xh plus h squared. When I plug in 0 for h, these two guys go away, and I'm just left with the first term, 3x squared. So let's do this one more time. First of all, we're going to see that as the power of x gets bigger and bigger, the limit becomes more and more annoying. But also we're going to see that a pattern is emerging, and we're going to see that that pattern is correct. So let's take the derivative of x to the fourth. By definition, that's the limit as h goes to 0 of f evaluated at x plus h, so that's x plus h to the fourth power, minus x to the fourth over h. When I multiply out x plus h to the fourth, I get x to the fourth plus 4x cubed h plus 6x squared h squared plus 4xh cubed plus h to the fourth minus x to the fourth all over h. That's a mouthful. Anyways, the x to the 4 and the minus x to the 4, they cancel out just as we've seen in the prior examples. And whatever's left has a factor of h that I can pull out, leaving me with 4x cubed plus 6x squared h plus 4xh squared plus h cubed quantity times h over h. My h's cancel, leaving me with 4x cubed plus 6x squared h plus 4xh squared plus h cubed. When I plug in 0, these last three terms go to 0, leaving me with 4x cubed. So here are our results. Using Leibniz notation, the derivative with respect to x of x squared is 2x. The derivative with respect to x of x cubed is 3x squared. The derivative with respect to x of x to the fourth is 4x cubed. Look at these numbers, 2, 3, 4. Also look at the powers. Technically, x is x to the first power, x squared, x cubed. Okay, so the number in front looks like the power of x, and the new power looks like 1 less than the power of x. So I bring the 2 down, and I reduce the power by 1, bring the 3 down, reduce the power by 1, bring the 4 down, reduce the power by 1. Generally, this suggests the power rule, which says that the derivative of x to the nth power is n times x to the n minus 1 power. So I take n, I bring it down in front, and then I reduce the power by 1. That is the power rule. Just to give you the idea behind the power rule, let's see what happens. When I look at the term x plus h to the nth power, it turns out that there's a formula for multiplying that, and it gives x to the n plus n times x to the n minus 1 times h plus a polynomial which is divisible by h squared. So really a polynomial times h squared, a bunch of terms that have h squared or higher powers of h there. So I can factor out an h squared from that polynomial. When I put that into the expression inside the limit, x plus h to the n minus x to the n over h, subtracting x to the n gets rid of this x to the n, and I'm left with n times x to the n minus 1 plus a polynomial times h, and I can factor an h out. there's a power of h on n times x to the n minus 1h, and I can take one of the h's off of here, pull that out. So inside, again, I'm left with n x to the n minus 1 plus a polynomial times h. That's all divided by h. So these h's cancel, and I'm just left with n times x to the n minus 1 plus some polynomial times h. As h goes to 0, the polynomial approaches some limit. This is 0. That goes away, so I'm just left with n times x to the n minus 1, which is what we said. So let's apply the power rule. So let's take the derivative of x to the fifth. The power rule says that since this is just a power of x, I can take the power down and put it in front. So I get 5 times x to the, well, I take this power and I subtract 1, so x to the 5 minus 1. 5 minus 1 is 4, so I get 5 times x to the 4. If you'd like to be careful, you can write out this step in the middle where you explicitly subtract 1 from the exponent. However, you don't need to. For example, the derivative of x to the sixth is, I take the 6, bring it down in front, then I take 6, reduce it by 1 to 5, and I just write 5. Great. So your first question is to evaluate the derivative with respect to x of x to the 100th power. Now the power rule still works with exponents equal to, say, 0 or 1. This is just a tricky point because we typically don't write x to the 0 and x to the 1. Because when I write x to the 0, well, x to the 0 means 1. Anything to the 0 power is 1, except for possibly 0, but we just define x to the 0 to be 1. Well, what is this? It's a horizontal line. So its derivative is 0. Everywhere its slope is 0, its derivative is 0. The power rule would say the derivative of x to the 0 is 0 times x to the minus 1. 0 times x to the minus 1 is 0. That checks out. X to the first power is just x. That's a line with slope 1. So its derivative is 1. Well, the power rule would say x to the 1, its derivative is 1 times x to the 1 minus 1 is 0. 1 times x to the 0 is 1 times 1. X to the 0 is 1. And 1 checks out. Great. So the rule still works here. Now, the great thing about the power rule is that it works with any exponent. It doesn't matter if it's a whole number, positive, it doesn't even have to be a rational number, it can be any number. So let's differentiate three functions. First of all, let's take f of x is 1 over x squared. We need to recognize when I have a reciprocal power of x, the best way to differentiate it is to rewrite it as a power of x in the numerator. So x to the minus 2 is the same thing as 1 over x squared. I apply the power rule. I bring down my negative 2 when I differentiate. Then I take 1 away from negative 2. A common mistake is to think that negative 2 minus 1 is negative 1. I like to explicitly write it out in this case just to make sure I don't mess it up. Negative 2 minus 1 is negative 3. So negative 2 times x to the minus 3. If you want to make it look a little more pretty, you can put that down into the denominator, negative 2 over x cubed. We can also deal with roots now. Let's take g of x as the cube root of x. We have to remember that when we're doing calculus, it's best to write our roots as powers of x. So the cube root is the 1/3 power. The power rule says when I take the derivative of g, I bring the power down, which is 1/3, then I reduce the power by 1, 1/3 minus 1, which is negative 2/3. And if I want to make this look a little nicer, I can put that into the bottom. I get 1 over 3x to the 2/3. Finally, what about something that's not even rational, like the number pi? I cannot write pi as a ratio of two whole numbers. I can approximate it, but I can't write it exactly. So how do I take the derivative of x to the pi? I bring pi down. I subtract 1. I can't do any better because I can't write pi any nicer than that, or pi minus 1. So that would be the final answer